Today, almost the entire class is going to be ordinary differential equations. It's going to be almost a whole class on MATLAB, and my intention is for this to be somewhat of a review class. It's not going to be too fast. I want basically everybody to follow everything. I don't want you to be busy taking notes. There will be video you can look at. I want you in the here and now to understand what I'm saying. So I would like you to get out of the frame of mind that you will learn it later. It looks like it might make sense. I'd like you to be right here, right now, following everything I do. So a lot of what I'm going to do is going to be reviews. For some of you, I'm not going to say anything new whatsoever. This is a catch-up class. Okay. Just for context, where are we in the course? Recently, we've been talking about various things. So one thing we've been talking about is F equals ma, which is one of the great equations in mechanical engineering. A special case of it is F equals 0, which is statics. And this is important for how things accelerate and move. And one dimension is a special case. We're doing one dimension because I'm not indulging in the world of vectors too much in this class. And if we're lucky, the stuff we're going to learn with F equals ma, you're going to be able to plug into your project, which I'll tell you about in a little bit. We're also talking about power balance. And I've tried to tell you that this has a life of its own inside mechanics, and it also has a life of its own inside the first law of thermodynamics. They're subtly related to each other. We've been talking about gearboxes, and for the most part, you think of gearboxes as things which have an input motion and an input force, or torque, and an output motion, output force, or torque, and it's a passive device, passive in the sense that it doesn't supply energy. But hopefully it doesn't dissipate much energy either. So the simplest way to look at gearboxes as the approximation is that the power in equals the power out. We've also been looking at the properties of motors. And the two kinds of motors we've looked at is electric motors, which were in the lab, and muscles as motors, which I haven't really got to in detail, but I just said let's approximate muscles as being something like electrical motors. And they are something like electrical motors in that they can apply bigger force when they're stalled than when they're going fast, and they can only go so fast. And there's some curve in between. Then finally, the part which is maybe the most technically involved is this thing of ordinary differential equations, which is if you take this equation, F equals ma, the a is acceleration, which is the derivative of velocity. Velocity is the derivative of position. This force is either given to you or actually depends on the position or the velocity or the time. So this is then an equation that has derivatives in it. And what we'd like to know is the solution of that equation, meaning what is the velocity as a function of time, or the acceleration as a function of time. We're trying to find a function with that property. You can try to do it with pencil and paper, but whether or not you can do it with pencil and paper, we believe that the physical laws make sense. We believe we put things together in a way that describes the world. Something happens in the world, so the equation, something happens, so there is a solution, whether or not you can write it with exponentials or logs or sine waves or whatever. And so this comes to this feature of ordinary differential equations, which is that even when you can't solve them with pencil and paper, even when you can't find a formula, there still is a solution which you can find an approximation to with the computer. It's not an approximation to sines or cosines, it's an approximation to something out there in outer space, which is just the numbers as functions of time which make this thing true. They're functions, but doesn't mean they have a representation algebraically. That's a confusion lots of people have. So here's where we are overall. These are all different things that you can think of somewhat independently, but they smush all together when you're dealing with something like the motion of a car or an accelerating bicycle or an accelerating electric car. Which gets me to the next thing, which is the lab. From this point on, that's today on, the lab is entirely based on this final project, which is a final competition. So you will build, using a motor, the same one you tested in the previous lab, a little car, and there's a race. And the race will be on Saturday, just after the last day of classes at 9:30 in the morning. And you'll all be competing with each other. And then your grade on the project, that's your 5 lab reports put together from these past 5 weeks, the last 5 weeks, is your description of the car. So your goal is to make a good car and describe it well and in sensible ways. What's the competition is with that motor and 4 AA batteries. You want it to go as fast as possible, 15 meters, and you want it to pull as hard as possible against other cars, and you can change around your car between those two competitions. And the rules are all spec'd out, and to the extent that they're not all spec'd out, we'll refine them if you have questions. Okay. Any questions about the overall plot line in the class, where we are, what's happening? Somebody just asked some question. Yes?
How big are the teams?
Teams are going to be 3 people, and the TAs are going to assign them.
They're in.
What?
They're in teams.
You ask a very pointed question. I told the directions I gave to the TAs are that they should pick the teams so that to the students they feel random, but if they think there's certain mixtures that are good or bad, they should go ahead and make them. So the TAs are told to tell you that they're random, but they might not actually be. Okay, so you can see, since only one TA is in the room, you get to see how good the other TAs are at deceiving you. I cannot tell a lie. It's tough. You ask me the right question, I have to give you the direct answer. Any other questions? Okay, so here we are in the world of ordinary differential equations. And they're called ordinary differential equations as opposed to partial differential equations because we only have one independent variable, time. We're not talking about derivatives in x and y or x and time, but just in time. So we're dealing with functions of time. So let me give an example of an ordinary differential equation. An example is that we want to find some function of time. Let's say x is equal to x of t. If you're a math type, you can't stand this notation. You write x is equal to some function of t, but that adds an extra letter, which we don't need. But mathematicians hate this x equals x of t thing. Anyhow, so we have x as some function of time, and we would like it to be one that satisfies some ordinary differential equation. And let's say the ordinary differential equation is x dot equals x. That's a simple differential equation. It says we'd like to find some function which, as a function of time, this dot means dx dt, as a function of time is equal to itself. The derivative is equal to itself. And we'd like it to satisfy what's called the initial condition. You have to say how things start and what the rules are for the change. That's this view of differential equations as being a crystal ball that predicts the future. You say, I know the state of the world, I know the rules of change, I predict the future with the differential equation, but you have to describe the state of the world, how things start, and let's just put in the initial condition that x at time equals 0 is equal to 1. So our goal is to find a differential equation that meets these conditions. So some of you might know a function that meets these conditions and know how to write it in some pencil and paper way, but we're going to pretend we don't know how to solve this with pencil and paper. Okay, so first thing, let's click in. And second thing is I want to play a little song for you. Who knows how to use iTunes? There we go.
I met this guy, and he looked like he might have been a hat check clerk.
We got to start all over again here.
Which in fact, he turned out to be.
Okay, I guess you got to hear the beginning.
I met this guy, and he looked like he might have been a hat check clerk at an ice rink. Which in fact, he turned out to be. And I said, oh boy, right. Again. Let X equal X.
Got it? Okay, that's all I wanted to get. Got it? Key equation. So this is, let's just check in here, and we'll do a little vote. Question 1. Have you ever heard that song before? Yes? No. No. Two people, just a minute. 2 people have heard it, that's pretty good. One person. I'll ask afterwards what strange event made it so they heard that. Okay. So every equation is that equation in disguise. So here we are for a differential equation. We've got a quantity we think of v. The v is the rate of change of x, but we want to think of it 2 different ways and then match them up. One way is we know that v is the rate of change of x. The other is that we've got some rule for the rate of change of x. In all equations you can think of this way. The same thing you think of 2 ways. Okay, so now given this, how do we find such a function that has this property without thinking about guessing the solution? By the way, how many people know the answer to this question as a formula right now? Yes? No? Okay, but we're pretending we don't know the answer. So how are we going to solve this thing is we want to use this crystal ball view of what differential equations are. So there's some function of time. We don't know what that function is, but we know that at the beginning of time, or when we start the universe, and we start looking at the world and how its rules evolve, this function has the value of 1. So this is a statement here that x of 0 is equal to 1, like that. And then what we're told is at that time, we can calculate the rate of change, because on the right-hand side of the equation, we're told the rate of change. We're told the rate of change in terms of x. So we are told that whatever this function is, it has a slope of 1 at this point. So this says that x dot, when, I'll make a little table here, x dot, when x is equal to 1, x dot is equal to 1. So we know whatever this curve is increasing at the rate of 1. Then we can say, let's go forward a little bit in time. And what we can do is go forward a little bit in time. And usually this little bit of time, people call this h, this little bit of time, or they call it delta t, the little bit of time that you're going to advance. And we say, well, approximately the function goes up to here. Now that's not exactly right, but it's close to right if h is small. And the not exactly right is why this is a numerical approximation. Now we've gone up a little bit here, and the slope is a little bigger. What's the slope at this point? Well, we can evaluate x at this point. Here it is, the new value of x. In this case, is x plus h if we've worked our way down through the system. So the slope is now x plus h. And then we go up here a little bit. Then the slope is bigger. And we go up here a little bit. And the slope is bigger. And we go up here a little bit. And we can set out in these increments, always finding out what this function will be in the future. Now, if we did this whole thing again with smaller time steps, we could do the whole thing starting at 1, and we just go a little bit, and we'd get a slightly different curve. And we could take smaller and smaller time steps, but eventually we get to some curve in the limit as h goes to 0, which we think of as being that curve, the right curve. In the same way as when you do numerical integration and you use the left, what do they call it, the left side rule? What's it called when you do the boxes on the left or the boxes on the right? What? The left-hand rule and the right-hand rule. They give 2 different answers. If the function is monotonic, one of them is necessarily bigger than the right answer, the other one's necessarily smaller, and they squeeze into the right answer as the step gets smaller and smaller. And this also squeezes into the right answer as the steps get smaller and smaller, but we don't have 2 methods. Actually, there are 2 methods like this, and there actually is a left and right method, but I don't want to get into that. So we just have one method that converges to the so-called right answer. And so when you talk about a differential equation, you talk about the solution, even those people who are really mathy and formal, this is actually the definition of the solution. The same way that the Riemann sum is the definition of an integral, the definition of a solution of a differential equation is what you get in the limit as h goes to 0 when you do this process. Now, if you're not taking the limit, this is a method of approximately solving a differential equation. So like the Riemann sum defines an integral, But separate from the limit in case of the Riemann sum, it also gives you a method for approximating the integral. This gives you a definition of the solution of differential equations, but without taking the limit, it gives you an approximate solution of the differential equation. But it just uses this idea that the differential equation tells you the rate of change of variables in terms of their present values and the time and anything else, and then you move forward because you know the rate of change. Then you have new values, move forward, new values, and so on. And that's the idea you'd like to get in your head for numerical solution of differential equations. So now I'd like to take this idea for this function, plug it in the computer, look at what we get, and then I'm going to go on and do harder examples that are more like mechanics. Here we only have one dependent variable, x. Always in mechanics problems we have at least two. Why? Because we have both x and v changing in time in ways that we have to keep track of. Here x and v both change in time, but the rules are self-contained if all we do is look at x. We don't need to look at the rules for v. Any questions so far? Okay, so now I want to go into the world of MATLAB and go on. Anoop, the question is can you see the font on the board? What I'd like is for them to not take notes and know that they can come back and look at this video. They can't. I don't want to send them a file because the file will be evolving in time, and so there won't be a record of it. You think they can read the font here? At least it's not noisy. What do you think? Should I let him go, or should I ask him to stop? All in favor of letting him go? Okay. The poor guys that got to make a living. Okay. Okay, so we're going to try and solve the differential equation. So for our differential equation, let's pick a time interval. Let's call it t. And for this case, I'll take a time interval of 1. So that way, when I'm changing numbers, all the numbers I'll change will be at the top of my file. Here's a script file I'm going to solve the differential equation. Let's take a number of points that we're going to use in the solving the differential equation. And I always like to use like some even number plus 1. Why is that? Is because the number of intervals is 1 less than the number of points if I have a point at the left interval or the right interval. So I've got my time interval. I've got this n is 1. I'm going to be looking at a sequence of times. So I'll look at a sequence of times, which will be a linspace. For convenience, I'm just going to assume the starting time is 0. You don't always have to use a starting time of 0, an end time of time, and n points like this. Now I've got a vector of t, 101 numbers t, that range from 0 to 1. So it'll be 0, 0.01, 0.02, all the way up to 1. That's what that list of variables, little t, is going to be. Now I want to make my solution of my differential equation. And to start with, I'm going to fill in the solution and pretend it's all zeros. So I'm going to, basically this is making space in the computer memory for all the answers that are going to be there. And I'm going to make this in a matrix, which is 1 by n, which is my solution. This is where the solution of the differential equation is going to sit. Corresponding values of x will correspond to corresponding values of t. I'll put in my initial condition, and my initial condition is that x of x sub 1, the first value of x, is going to equal to 1. So this is what I called my initial condition for the differential equation. So I haven't yet said what the differential equation is, but these are little things that are setting up to solve the differential equation. Some of these things will become clear as I go on, so unless I made a mistake or you have some very specific question, I'll let you ask questions, but I just want to write more so context is clear. You can read the board, no problem? Okay. Now we want to solve the differential equation. So to solve the differential equation, we've got to set up a loop to solve the differential equation. So I'm going to go for I is equal to 1 up to n. And then I'll have an end, which is the end of my loop. So this is a syntax of a for loop. It says go do whatever is inside the set of instructions over and over again. Start with the value I equals 1, then the value I equals 2, up to the value I equals n. Now, someone pointed out to me yesterday that in the tutorials, that the tutorial lessons, there's no lesson on loops. In the introductory text I gave you, there's no lesson on loops. Some of you have never had programming before and don't know anything about loops. So do what I do in situations like this, and you go Google MATLAB tutorial loops, and you type that in, and it gives you a thing that says loops in MATLAB, and you type it in, it says MATLAB tutorial on loops, and you read this through, and then, for example, one of the examples in here happens to be how to solve differential equations in MATLAB using loops. So it's all set up for you, and you can probably find, I'm guessing, 20 other tutorials on loops on the internet. Okay, so here we're going to write this loop. It's going to be a for loop. What are we going to say? We're going to say that the value of x at, now we're starting at I equals 1. We're only going to go up to n minus 1 because we're only having n intervals. Remember, there are n points, but there's only n minus 1 intervals. So we'll now say that x sub I plus 1 at the next time, the value of x is going to be what it was at the previous time. If we know what it is now, we go a little bit into the future, and then we multiply by this time interval, h. Well, h is sort of implicitly defined by the time interval and this n up here, so let me just make it simpler. H is then equal to t divided by this quantity n minus 1. So it makes the code look a little simpler if I just calculate the h up here. So I put here plus h times the rate of change of x, which is going to be v. And just to make it clear, let me just put here what the differential equation says. The differential equation says that v is equal to x. So this is the differential equation, if you like, the right-hand side of the differential equation. And this then is one step in Euler's method, which we're going to do over and over again. Having done that, we now might want to look at a solution. We might want to plot the solution. We've solved it now. We've got the initial condition in here. We've got the solution, and we can make a plot of, for example, t on the x-axis and x on the y-axis. If we want to make it so that we can read what we're doing, we put title and we put solution of ODE, and I should put my name here and stuff like that, but I don't want to type too much stuff, and we're done. And we can type this. We can type the execute command, which up here in debug it says save and run demo. Instead of doing that, I'm just going to hit function F5, and I get my plot. Okay, and it's got to look something like what I wrote before. It says A and B, number of elements in B and I must be the same. Okay, so where is my mistake? It says V equals X. And x, remember, was this whole giant list of numbers, and I meant v equals x sub I, and that's velocity at this time. If I wanted to save it up, I could put v sub I, but I don't need to bother. Okay, let me try again. There's my solution. It's too much chatter there. I should have put a semicolon here. Let me try again. Okay, less chatter, and then I get this plot. So there it is starting at 1. You don't see a 0 over here on the left-hand side because the MATLAB rescales thing is kind of a bad feature of MATLAB. If you want the solution to be a little more intuitive, you would put axes, and I would put what I want for my x-axis, which I want it to go from 0 up to t, and my y-axis, I want to go from 0 up to, well, let's just put it up to the maximum value of x. And so this would give axes that scale the thing a little bit more nicely, if I got this right. Yep, and then I get something which starts at 1 and goes up to the maximum value of x. Okay, here's the whole code. Now, I want just nothing but questions for a little while. Everybody in the class should understand everything on the screen. Okay, and for the purpose of the video, I'll stand here and point to things so you can zoom right in on this video, Anoop. Okay, any questions?
Why did you do v equal to x of I?
Why did I do this? Because I want to say, in general, the next value of x is the previous value of x plus the rate of change. I could have put in here x, but I want to be able to put in anything I want over here for the right-hand side. So I'm just separating out what is the right-hand side of the differential equation from the fact that I could put anything here?
I still didn't get how you got like the thing. Like, why is there a v in the equation, and like why is v equal to x? Why?
Okay, I could let me just write it maybe in a better way. Let me call this right-hand side, and let me just put over here right-hand side. So the differential equation has a right-hand side. I could have put x dot equals x. I could have put x dot equals x squared. I could have put x dot equals anything I wanted. So I'm saying whatever was on the right-hand side, let me put that up here separately so that you can just see here is Euler's method in one line, which says the value of x at a new time is the old time plus whatever was on the right-hand side multiplied by the time interval. I could put whatever right-hand side I want here. I could consolidate these two lines into one. I'm just trying to make it more clear that any right-hand side, that Euler's method is all encompassed in this line no matter what I put on the right-hand side. If I put over here x sub I or x sub I squared, it would be a different case for every different solution of the differential equation. Does that answer your question? Okay, your question? Up here? Okay, so MATLAB, remember MATLAB, the MAT in MATLAB stands for matrix, and it's got tons of commands for dealing with matrices. So a command in MATLAB is the zeros command, and the purpose of this command is to make a whole list of zeros. And it makes an array of zeros, and this says how many rows and how many columns. So this makes a big, long a list of zeros. Why do I do that? Is so I can fill them in with the right values here. Now it turns out that this code would run fine if I left this line out altogether, and MATLAB would figure out that I've got that, oh, x is just a list of one number, then it says, oh, you're asking for the next one. Oops, sorry, it's a list of two numbers. Oh, you're asking for the next one. Oops, sorry, it's a bigger list. But every time it does that, it has to go into the computer memory, allocate space, and it's much, much slower. So if you start putting numbers up here for n, like 10,000, 100,000, or a million, it will run way, way, way slower if you don't have a line like this, which basically allocates memory for keeping the numbers. Does that address your question? Okay. Any other? I'd like every other question, not any other question. Yes? Say again?
If instead of using the zeros command, you filled it with another number, does it matter?
I actually could fill it with absolutely anything because I'm overwriting whatever is in there down here. So for these purposes, I could fill it with anything. I'm assuming that it's a little faster to fill it with zeros than anything else. There is a MATLAB command called ones, where I could fill it with ones here. But I could do whatever I wanted and fill it with anything I wanted if I had some other way to do it. Yes?
So since you set the initial value equal to 1, if you did use 1, you'd be able to leave that line out, right? The x of 1.
If I'd use ones, I would happen to be able to leave this line out unless I change my initial condition to the starting value is 2, or a half, or it's 3/4. Here I separate out my initial condition from my initialization of the matrix. Yes?
What if the initial condition was 0?
If the initial condition was 0, well, just everybody think about it, especially you guys in the front row here. What if the initial condition is 0? What's going to happen here? Okay, everybody thinking about it? Who has an answer in their head? Raise their hands. Who doesn't have an answer in their head? Okay, talk to each other. 15 seconds. Talk to your neighbor. This is not just slightly reminiscent of what we were talking about. It's exactly reminiscent of what you were just talking about. Right? Well, it's not exactly. It's just slightly.
Oh. Okay.
Okay, who has an answer now? Raise your hand. Don't have an answer? Come on. This is not hard. Differential equation says the rate of change is equal to the current value. You start out at 0. What's the rate of change? 0. So what's the value at the next time interval?
0.
And then the rate of change is what? 0. And the value at the next time interval?
0.
And the rate of change is what? And the next time interval, 0. So what do we get? 0, 0, 0, 0, 0. If you have something which grows in proportion to its initial size, but it starts out with no size, it ends up with no size. So you plug in your brains and you get 0. And the computer agrees. Okay, next question.
So how do you fix it later at 0?
How do I fix it?
Like, a lot of times.
If it ain't broke, don't fix it. This is the right answer to this question.
No, but like, what is the position if a particle starts from 0 and then like moves?
Well, it does. If it starts from 0 and then it moves, it's not following these rules. If it's following these rules and it starts from 0, it doesn't move. If it starts from 0 and it moves, then this is the wrong equation. We fix it by saying, oops, we made a mistake earlier on in the problem. Over here, we're fine. Okay, everybody's supposed to understand everything on the board. No question is too stupid. Yes?
When you have x at I plus 1 equals x, is that the function line? Is that just saying that your like the xi term is like previous term, and then you're adding like the slope of the next term to it?
That's correct. So this line right here says, going back to this picture, Anoop, can you come over to this picture? Here we are, say at the third time step. So here's this corresponds to I equals 3. We've gone over here to t equals 3h. We know the current value of x. This would be x sub 3, which is x at this time. At this time, we can evaluate the slope. That's the right-hand side. We look at that slope. We multiply by the next value of h, and it tells us the new value of x. So here's a 1. Here's the right-hand side, the slope, and it's telling. And that equation, that one line, that second line inside the loop, tells you that the new value of x is the old value of x plus the slope times the interval. Who asked the question? Does that answer your question? Okay. Next question. Yes?
Isn't it the left-hand slope since you're starting at the most left and you're going one?
This is what you could call this the slope. So the differential equation says at every instant in time, the slope is supposed to equal the value. And we can't do that exactly on the computer. So we say, right here the slope is equal to value. Let me just use that slope for a while, even though it's not quite the right answer all the way through. Just like you use for the left-hand method. What's it called? What do you call it? The left, no, for integration with the left-hand sum. So it's like the left-hand sum for integration. It's not the right answer. It's just an approximation. We're a little bit off. If you want to look in detail here, the exact solution is some curve like this. We're going here like this. We're using this value of the slope and extrapolating, and we're getting to here when we should have got to here. On the other hand, if we took a smaller time interval, we would have got to here. The next time we'd get a slope like this, it would be closer. And if we took a smaller one, we'd get to here. The next one we get to here. The next one we get to here. The next one to here. It would be closer. So the smaller we take h, the closer we get to the right solution. Just like for integration, the smaller you take h, the closer the left-hand sum comes to the correct answer. Does that answer your question? Okay, keep going. More questions. Yes?
Why don't you need to define h before you use it?
I did. I defined h right there.
Okay.
Is that okay?
Yeah, I think so.
Next question.
Why do you write the right-hand sum or whatever it is? Why do you have to define it? Why don't you put x?
Why don't I put what?
Why do you put that? Why don't you just put x and y in there? Why do you have to define it separately?
Why did I put this here? I could have just put it in here. I could have. The reason I put this separately is that if I had a different differential equation, say x dot is equal to x squared, or x dot equals the square root of x, or x dot equals t, or x dot equals a constant, or this part, which is Euler's method, all written in one equation, can stay the same, and I have the change in the differential equation up here. So I do that to separate out the method of solution from the actual equation of solving. So it's a programming rule of thumb, is even though you can consolidate things into big equations, it's actually easier to read oftentimes if you keep ideas separately like that. Does that answer your question? Okay, keep going. More questions. Do you understand absolutely everything on their board?
For the most part.
I want every single line on there to be clear. Yes? Yes? We're finding there is some curve. So this is what we say is, if we write this equation, dx dt is equal to x, and x at time equals 0 is equal to 1, this is an implicit description of some curve. There is some curve with that property. There is some curve that solves this differential equation with this initial condition, and we're trying to find that curve. So we're trying to find that. What is that function of time? What do we mean by a function? We mean a list of pairs of numbers, x and t. An infinite list of pairs of numbers. We can't find that infinite list of pairs on the computer. We can only find an approximation. So this has some exact solution, like that, and we're trying to find a set of points which is pretty close to that. That's the point of the exercise. Does that answer your question? Okay, keep going. More questions. Yes?
Why do you start I at 1 as opposed to starting I at 0?
We could have started I at 0 if MATLAB worked like that, but the way MATLAB likes to, when you create an array of things, it thinks of the first thing in the array as being 1. So it's a list of numbers. The first number in the list has a value of 0, but the first, if we itemize it by the index, by say t sub I, which means t parentheses I, and we put t sub 1, the first one in the list is 0. So conceptually, you think of it as a 0th one, but MATLAB doesn't make lists like that. Now, I think C defaults to index of 0. Is that correct?
Most languages do.
What?
Most languages do.
Most languages use 0?
C and everything.
But not maybe most modern languages. Fortran, MATLAB, the ones in the numeric tradition start with 1. Just like because they're meant to mimic mathematics, when you have these sums, capital sums, usually you start with an index of 1. But it's just a convention that the language uses. Yes?
Why did it work when you had the initial condition of x at 1 equals 1? I thought the initial condition was x at 0 equals 1.
Okay. It's x at time equals 0 is equal to 1. But at time but MATLAB doesn't. We're trying to find x of t in math speak. In MATLAB speak, we're trying to find a list of values of x. So the numbers which go in here are which element it is in the list, not the value of the time. So if we want to find the corresponding value, and let's say if we put x sub 7, that corresponds to x at t equals t sub 7. So we have these two lists, x and t, which are indexed 1, 2, 3, 4, 5, 6. If we want to find the corresponding values, we look at the 7th element of both lists. Very good question. Very good, easy, very easy thing to be confused about. Yes? Let's say we want to know the actual solution in algebraic form. Okay, so in this case, we can find it. We can find it using separation of variables. We can find it by the method of guessing. We can find it because you know the solution. You can find it by intuition. But for most equations in engineering practice, you cannot find the solution. So not only can't you find it, but I can't find it. No mathematics professor at Cornell can find it. No mathematician in the history of the universe can find it. Most differential equations just do not have formulas for their answer. There's some curve for the answer, but there's no formula for it. So the best you can do is find a numeric approximation. Now, in this case, half the class knows what the formula is, and I'm going to test their knowledge by a little exercise here, and then I'll go back to take more questions. So if I put a 1 here, then I put here the command x sub end. The word end in this case is the same as putting x sub n. It means take the last value of x. So end is a MATLAB command, which in this context means takes the last value. What is the output of this going to be? Don't yell it out. Think to yourself. What the answer is, I want you to talk to each other for a minute. Talk to each other. Talk loud, loud, loud. So I'm going to run this program, and I want to know what the result of this command is going to be. Talk. More noise. Talk, talk, talk. Do you understand everything? Not just approximately, totally. Everything. You're supposed to understand every single thing. If you don't, ask a question. The reason I picked on you is you looked a little isolated and dazed over
You do x of
here.
n, I know that. You wouldn't do x of n, you would do x of I.
Okay, 10 seconds left. Okay, done. Who has an answer? Raise your hand. What's your answer? E. Is that your final answer? Exactly E. Is that your what? Who knows what E is as a decimal expansion of E? Let me hear some numbers. 2.71828. What are the next four digits? 1828. Okay, 2.718281828. That's one guess here for the solution. Let's see what happens here. Function f5. 2.7048. Is that E exactly? Not so good. Okay, so what happens if I put here not 101, 1001? Do it again. Now I get down here 2.7169, a little closer. How about instead of 1001, I do 10,001. Run it again. 2.7181. That's pretty close to 182. Okay, let's not do 10,001. Let's do 100,001. What am I asking MATLAB to do? I'm asking it to do that little draw straight line segment, so I'm asking to do it 100,000 times. Okay, amazing what computers do nowadays. 2.7183 looks like it's getting closer. I go format long. Let's look at some more digits. Let's run this again with more digits. And I get 2.71826. Pretty good. Let's ask it to do it 1,000,001 times. 1,000,000 times I'm asking it to do this arithmetic. Maybe you guys aren't amazed by this stuff anymore, but there it is. It's getting pretty close to E. So the smaller we take H, the smaller this converges, closer this converges to E, because the solution of this differential equation is x equals e to the t. And if we plug in t equals 1, it should be x equals e. So it's coming out closer and closer to the right solution as we take more and more steps. What happens if we do this 10,000,001 times? Can we do it 10,000,001 times? It's busy. Amazing what computers can do. Yes? What? On a Macintosh, you can find it on your PC by going under debug and see run the file here, and it's F5. And it happens the way my Mac is set up. I have to hit function F5. I don't know. It's something about something I set up. I don't remember what it was. Okay. Any more questions about what's happened here so far? Yes?
Is x of n the value where
X of n means the last value of x, which is number 101, which corresponds to t sub 101, and t sub 101 was this value of t, which is t equals 1. It's the last one. Yes?
If we had a differential equation, would we just change the initial condition and what RHS is?
Well, let's just do a really quick one here. A really quick one is I could put a minus sign here. Let me not make MATLAB do quite so much work so we don't have to wait for it. Then I'm doing x dot equals minus x. It means the rate of change negative is proportional to the function. I run that. I look at the plot I get, which is somewhere on the screen figure, and I get exponential decay. If you don't think it looks much like exponential decay, let me put a longer time here, 5, and then look at this as exponential decay. But I could put other differential equations here. Instead of putting minus x, I could have put minus x squared. It's a different differential equation with a harder solution. Who knows what it is? I don't know. But it looks like that, the solution to it. Okay, I could put plus x squared. Now if I put plus x squared, I got to watch out for it, because I'm likely to get an error here. Let's see if I get an error. It blows up and goes to infinity. So what happens if I want to look, let me just put, instead of t equals 5 here, t equals 0.9. This happens to be a function that really takes off. Once it starts to get big, it gets really, really, really big. So if I put 0.99 here, it's way up there, going on its way up to infinity. Okay, so differential equations can blow up to infinity. Okay, now the same idea is going to work when we go to mechanics problems. In mechanics problems, we have a differential equation, which is F equals ma. So we have a differential equation F equals ma, but I think of that as being the differential equation F equals mv dot, and so I turn that into v dot equals F over m, and then I have x dot equals v, and this is now a set of differential equations if somebody tells me what the rules for F are. So if I have the rules for F, I have these two differential equations, and let me try to solve these differential equations using the same method, all very quickly. I only have 4 minutes to do it. But it's not that hard. How's it going to go here? Well, I have t set up. Now I have my x's set up as a bunch of zeros. I'm going to set my v's, all the different v's set up as a bunch of zeros. I've got my initial condition for x. I've got to put in an initial condition for y, for v. So I'll put v sub 1 equal to something or other. Let me just put 0 here. In my differential equation, I'm going to have my rule for f. And there are various rules I could put for f. A nice rule for f is that it's minus x sub I. The force is proportional to minus the position. Then I have x sub I plus 1 equals h times, and now I'm going to put v sub I, because the rate of change of x is the velocity. And I'm going to have v sub I plus 1, almost exactly the same line, but not really. V sub I sub 1 is v sub I plus, now I have the rate of change of v, but that was F divided by m, and F is the force in the mechanics equation. So now I have some mass somewhere defined here, so I've got to say what's my mass for my physical system. So let me just put in a mass of equal to 1 up here. And now I've got, let me put a longer t up here of 3. I need to change this x into a v. And now I've got exactly the same rules. It says the new value of x is based on the old value of v. Where you are is where you were plus how fast you're going. Yeah, everybody knows that. You're not going fast, you don't go very far. You're going fast, you go far in a little bit of time. And the new value of velocity is the old value of velocity plus something proportional to the acceleration. And I just march through time with that, and now I can look at the x and time I get out of this. Now, does anybody know what I'm going to get from what I just wrote here? Well, what is this problem? It says that, Anoop is smiling, he knows what the answer is. Okay, it says that the force on something is in the minus x direction proportional to how far x is. And I started over here at x equals 1. And I started over here at 0 velocity. So it accelerates that way. It goes faster and faster that way until it gets to this side. But now the force is minus x, but x itself is negative, so it accelerates that way. So it goes back this way, and then it goes back this way. And when we run this thing, let's see what we get. We run this thing, function f5, and we get the solution. Now, I didn't get the minimum value of my plot here, so let me put the minimum value of x to make the plot show everything. And I get, look at that. And 6 is very close to 2 pi. If I put 2 pi here, it would come out exactly in oscillation. Let me put here 20 so you can see more of it. What is this? This is a harmonic oscillator. Just like that. We didn't put any sines or cosines in it. MATLAB doesn't, for the purpose of this problem, doesn't know anything about sines and cosines. It just knows the rules for looking forward in time. If you know the position and velocity, we put in rules for how the position and velocity evolves. The position evolves by saying the new position is the old position plus how fast you're going times a little bit of time. The new velocity is the old velocity plus the change due to the acceleration. The acceleration is due to the force. In this case, we put implicitly in, by the differential equation, a force which is proportional to minus the position. That's the restoring force of a spring. I could put other forces in here. I could put as minus x sub I, and I could also put minus v sub I, which says that the force is proportional to the velocity, or the velocity squared, in the case of the homework problem you have due Friday. Then I get a damped oscillation if I put in minus velocity. I could put the force as proportional to the position. That would be like a ball falling off the top of a hill. When I do that, it takes off, goes faster and faster down the hill. The farther it is from the top of the hill, the bigger the force. If I take away the damping term, this minus v, then it will go even faster. Any quick questions about this? It's all on the board. The video is clear up there, Anoop? Let's just take one question about this. One question, yes? Go ahead.
No, I forgot what I was going to say.
I was going to say, I'll give you all the money from my pocket, but I will not. I had some quarters in there. What did I do with them? I'll give you a quarter if you ask the question.
No, it was just I recognize that it was the motion spring.
Yeah.
What if you wanted to keep it cordial? And so you wanted to have like a variable k in there, and then you wanted to have the k reflected on the graph.
You wanted you mean you wanted the spring, a nonlinear spring?
Well, no. So you have when you had it just the original one, so that your key values were one.
I just put over here like this.
Yeah. So your key values are 1 and -1 or whatever.
This one.
Instead you want them to be k. Yeah.
But what do you want instead?
Well, if you say you had a spring constant that you just want to be a generic constant, that would
Well, I put a constant of 1 here. I could put a k times here, and I could put up here k is equal to 7, and now I've got a generic constant.
What if you don't know it's equal to 7? You just have it k, and you just want to see what the graph looks like just with k.
Oh, well, that's asking for something analytic, which this doesn't know. If you want to know what the result is as a function of k, you have to run it again and again for different values of k. By the way, just quickly here, notice that these oscillations are growing, but the mathematical solution doesn't grow. That's a numerical error. If I want to get rid of that error, I take more time steps, I put an extra time step here, and then that growth will get much smaller. It gets flatter. Okay, we're out of here. You can come up and ask me questions. Good luck on your homework.